Hello, my name is Rudi Poepsel-Lemaitre from the TU Berlin, and in this video I will give you a brief overview about one of our publications for the PLDB 2021. In the land of data streams where synopses are missing, one framework to bring them all. Let's start by motivating our problem. Data flow engines process streaming data by using a collection of interconnected operators called the processing pipeline. Until now, when a user wants to perform approximate data analysis using such a data flow engine, he usually constructs the synopsis with a pipeline operator. However, the analysis itself is performed outside the pipeline. Constructing the synopsis is very efficient and can be usually performed with very low latency. Nevertheless, we wanted to improve this technique to provide data flow engines with the necessary tools to support approximate data analysis fully. We had three questions in mind to achieve this. First, how to compute synopsis in a distributed system and fully exploit the parallelism. Two, how to adapt the synopsis operators with the other operators in the pipeline. And three, how to organize the incoming values meaningfully for later approximate data analysis. Based on these requirements, we designed a new framework called Condor. Condor allows for the specification of synopsis-based streaming jobs on top of general data flow engines. It also provides a collection of 12 synopses and an integration to Apache Flink. However, our techniques can be integrated to any data flow engine that supports window processing. Additionally, Condor provides the necessary interfaces so the user can integrate any new user-defined synopsis into our framework, and Condor will provide a scalable processing environment. Here we can see a general architecture of Condor, consisting of two main components, the API and the core. The API provides an abstraction which the user employs to write synopsis-based streaming jobs. Once done, the user submits this to Condor, where based on their configurations, the core creates a data flow pipeline of efficient operators with two processing blocks, the synopsis processor and the synopsis evaluator. Condor then submits this data flow pipeline to the underlying data flow systems for its execution. During the execution, the first processing block is in charge of consuming the input stream and generating the window synopsis. And then these are evaluated by the second processing block with a query string outputting the approximate results. Now, let us see the execution more in detail. We model synopsis as stateful window aggregate functions. Doing so enables us to maintain any one-pass synopsis in a distributed setting, as we can use the divide and conquer strategy. We also expand our model to classify synopsis by their algebraic properties, enabling internal optimizations such as parallel computation and accepting out-of-order elements. Condor splits the synopsis computation into three phases: divide, compute, and merge, and utilizes different processing strategies in each of them based on the user's configurations. Here, we will explain only the basic idea of each phase. First, during the divide phase, Condor distributes the input data stream among all nodes to fully exploit the available parallelism. After this partition, now the system can organize the incoming elements in windows, which are distributed among all the threads in the system. Our goal is to get a single synopsis for each global window, so during the compute phase, Condor maintains a synopsis for each partitioned window. Finally, once the partial synopsis has been created by Condor, it merges them without parallelism if both possible and global synopses are required. Our abstraction also allows us to support multiple windowing strategies. Condor already supports bucketing and general stream slicing, providing an hybrid solution that adapts the windowing strategy in runtime depending on the window's configuration. Now, after constructing the synopsis stream, the user can evaluate them using the operators of the underlying data flow system. However, Condor also offers a set of operators to efficiently evaluate the synopsis string inside the pipeline. Our operators follow the broadcast state strategy, where every synopsis is broadcasted to all partial instances of an operator, so that we can evaluate them against all the elements coming from the query stream. This way the system can query the same synopsis simultaneously on every thread, even as each synopsis was constructed only once. Now let us see how good Condor performs compared to one-off implementations and Yahoo DataSketches. We evaluate the features of our system by comparing it with custom one-off implementations of the count-min sketch in Flink. On the first plot, we observe the results of our serialization experiments. For these experiments, we maintain the parallelism of 256 and gradually increase the number of sources that simultaneously ingest data into our pipeline. We see that in cases where we have a single source, the serialization cost is so high for the distributed approaches that there is no significant improvement over a centralized approach. However, as soon as we increase the number of sources, the cost per tuple decreases, which makes the serialization pay off, outperforming centralized approaches by a factor of 25 for 256 sources. The second plot shows the performance when we increase the number of concurrent windows. The results show the benefits of combining different windowing strategies. We observe that only the case where Flink distributed has a similar performance as Condor is when there are no overlapping windows. However, the performance of Flink distributed drastically drops as soon as the streaming job has more overlapping windows. On the other side, Condor switches to general stream slicing when windows start to overlap, making it more stable even with an increasing number of concurrent windows. We also evaluated the efficiency of our summarization libraries and compared it with Yahoo DataSketches. Yahoo DataSketches doesn't provide connectors to any real-time stream processing engine. Still, we try to configure these experiments to be as fair as possible. We observed that Yahoo's implementation outperforms Condor only in scenarios with very low parallelism because of Flink's system overhead. However, we observed that already with 8 cores, our system achieves a better performance. More interestingly, we observed that Condor's implementation scales linearly with the number of available cores and outperforms Yahoo by more than 1 order of magnitude when using a parallelism of 256. It can achieve this to its divide and conquer design, making better use of the system's parallelism, while Yahoo's implementation computes the global sketches centralized. An essential feature of Condor is that it allows users to implement their own synopsis via a simple API. This way, the users can focus on the application logic instead of intricate internal details. We tested this feature by adapting Yahoo's hyperlog sketch implementation into our API, showing that Condor enables any mergeable synopsis to scale linearly with the parallelism. The results show major improvements in Yahoo's hyperlog sketch scalability and performance when using Condor. Now, Yahoo hyperlog sketch performance is similarly to Condor's original implementation, and more importantly, it scales linearly with the system's parallelism. This shows both the ease of use of Condor and its power to provide a scalable processing environment for any synopsis, making Condor a perfect complement to summarization libraries such as Yahoo DataSketches for real-world applications. Summing up our contributions, we defined a new way to generalize and understand synopsis as stateful aggregate functions that can be processed in parallel with the divide and conquer approach, even for non-mergeable synopsis. We classified the different synopsis algorithms for optimization purposes. This classification amplifies our model, taking advantage of their mathematical properties from every synopsis. We propose a new system to easily adapt our model to any data flow engine that supports window aggregations. And finally, we demonstrated the completeness and improvements of our system in comparison to the related works and custom one-off implementations. Thank you very much for your attention, and feel free to contact me if you have any further questions.